So hello and welcome to this TA session for week 3 for the course of Physics of Materials, which is an NPTEL course. The course instructor is Professor Pratap Haridas from IIT-M, and my name is Mohammad Tehseen. I am the TA for this course, and I am a PhD scholar in the Aerospace Engineering Department at IISc Bengaluru. So let's just wait for a few minutes to see if some participants join, and we will start in a maybe 3-4 minutes. Okay, so let's begin this session. I will join from my other device so that I can write some things which will be visible on your screen. And if anyone joins along the way, we will allow them to join the meeting. Okay, so I'll start presenting my screen so that you can see. And my screen should be visible now. Let me go to my notes. Okay, so the course name is Physics of Materials. This is an NPTEL course for the session 2025, for the August session I should write. And the instructor of this course is Professor Pratap Haridas from IITM, and I am the TA. My name is Muhammad Tehseen, and I am from the department of, I'm a PhD scholar in IISc, in the Aerospace Engineering Department. Okay, so we are in week 3. This is the third weekly session. And previously we have been discussing, so we started the first session with the motivation for studying this course, and then we gradually we started looking at the properties, different kinds of properties that are exhibited by the materials. And in particular, we looked at some of the thermal properties, like thermal expansion, how that arises from the like at the very atomic scale, and why do certain materials expand when we heat them, and why do certain materials contract when we heat them, right? Or at least what are the conditions that should be satisfied when a material which govern whether a material would expand or contract on heating. And then we looked at the property of conductivity, electrical conductivity. Uh, we looked at some of the experimental techniques that can be used to measure the conductivity of some material. It can be a solid, it can be some ionic solution which conducts electricity. So we looked at what are the different techniques, and when we should use a DC source, sorry, when we should use DC measurements, and why in certain cases that doesn't work, and we basically it becomes necessary to use AC rather than the DC current to measure the ionic conduction and all that. So and then we looked at how the measured data can be basically fitted to onto some kind of a model, a simple let's say a resistor or a resistance in parallel with capacitance, these kind of models. We looked at how we can fit the experimental data onto these models, and how we can basically determine the properties of a medium, of a sample based on this data. So today what we are going to do is we are going to look at the same property again, electrical conductivity, but the approach will be more fundamental and theoretical uh, than what we discussed the last time. Okay, so what we are going to look at in this session is the property of electrical conductivity. Okay, and then further, once we develop a model for thermal conductivity, we would try to basically extrapolate that or use that to develop a similar model for thermal conductivity of a material. And then based on the model that we develop, which can explain these two features of materials, we would like to understand how these are related to each other. Okay, because generally we may from our common experience, everyday experience, we know that usually, for example, if we talk of metals, they are good conductors of electricity, but at the same time they are good conductors of heat as well. So is there a direct relation between these two properties, and if so, then can we predict that relationship, or can we justify this behavior based on the model that we develop, right? And in particular, the model that we are going to develop is known as the Drude model. Uh, so we are going to look at the Drude model for electrical conductivity as well as thermal conductivity. Okay. Now, before getting into how to develop a Drude model, what we would like to do is we would like to basically develop tools that we need to finally write this Drude model for the conductivities. And the prerequisites in this case would be a little review of so there are two main topics that we need to be familiar with. First is called the free electron gas, uh, or inspired by the ideal gas behavior. And when we so for this discussion we are going to be mostly concerned about, and if we make any statements, those would be related to metallic solids. Okay, so the mostly concepts will be applicable to metallic solids. Now how is a solid related to ideal gas behavior? Why are we discussing ideal gas behavior at all if we are talking about solids, right? That's the first question. And then the second question is, what is this free electron gas? So we'll try to explain these two things, and then we would look at some interesting properties that come out of this correlation, and we will also solve some objectives today. The basically the problem set, we'll solve some sample problems that will help you to solve the assignments as well. So before I continue, I just want to make sure that I am audible. Uh, can can you please confirm if you can hear me?
Yes, sir.
Hello, am I audible?
Yes, sir.
So I think ye- okay, I think I can't hear you. Can you please confirm again if you can hear me? Okay, so we are going to continue. Let's continue our discussion on free electron gas. Oh no, first let's basically review what we learned about ideal gases in our +2 level, and then we'll try to motivate why we are looking at this picture and how we are going to use it to study the uh, conduction problems of metallic solids. So what is ideal gas behavior? Okay, so ideal gas behavior. So the main assumptions that we make while treating a gas as an ideal gas is that we assume that uh, that the atoms or molecules making up that gas, they do not interact with each other. Okay, so no interaction between constituents. Okay, and the second thing we assume is that particles or constituents are far apart, right? They are separated by distances which do not affect the motion of one, like the motion of one particle does not affect the motion of another particle. They sort of move independently. Okay, and so what are the conditions under which such assumptions are valid? So such assumptions are valid if the pressures are extremely low, right? So there's no pressure trying to bind the atoms or molecules together, so they can sort of move freely around. And second thing, this ideal gas behavior is valid when temperatures are high, right? So at higher temperatures, the predictions of ideal gas, they closely match uh, mm, with the predictions of like the behavior of real gases that approximates very well with the with that predicted by the ideal gas. It's again related to the fact that at higher temperatures, the molecules or atoms of that particular gas, they vibrate faster in space, so they don't, like the energy that is contained in their vibrations, they are so large that other forces like the van der Waals forces or other kind of forces between the atoms, they become negligible. So as a reason that and they also try to, because of the higher temperatures, they try to expand. So this again, the hypothesis becomes better and better as the temperature increases. So uh, why are we discussing this ideal gas? So the motive is that we want to model the free electrons present in a metallic solid as an ideal gas, right? In which case the atoms and molecules of a gas that we study in the ideal gas behavior, they are replaced by electrons, and we will try to find some average properties of electrons in when it is modeled as that gas. So for that, let me just briefly try to recall what all we have done in our, let's say, +2. So I won't derive everything here. I'll just write the equations and you can find the derivations in even in the class 12th NCERT book. So if we assume that this is some cubical block of length L, okay, and let's assume that this is the plus x direction. This is the plus x direction. This one is a plus. Okay, we don't need this direction. Let's call this direction the x direction. So then if we look at, let's say there's a particle present inside this box which is moving with a velocity towards the right, towards the plus x direction, with a velocity of let's say v of x, v sub x. Okay, and it will now, as it is moving, it will strike the right wall, right? As it travels, it will strike this wall and then reflect back. So this is an assumption that the collision between this particle and the wall, that's perfectly elastic. Okay, so it just strikes the wall and then returns back without you losing any of its momentum. Okay, so so how do we write? So this particle, which has the velocity v of x, this particle can be anything. It can be an atom, it can be a molecule, and in our case, finally, we will see that it will be an electron, right? So for now, if we look at this particle, what is the momentum that's carried by this particle, right? So we assume that the mass of this particle is m, right? Then its momentum will be written as, let me call that let's say some small p. Okay, small p represents momentum. Then the momentum will be mvx, right? Because it's moving in the positive direction. Now uh, once it basically goes and impinges on the right wall and gets reflected back. Now we assume that the wall doesn't move, right? That's consistent with our observation. If we take a let's say a cube made of glass and keep it in air, it won't start moving itself. So this so let's write the balance of linear momentum, right? Balance of linear momentum for the system. So what is the total momentum before the collision? Let me write before and I'll write after here. So what is the situation like before the collision? So before the collision, wall is stationary, right? The velocity of the wall is zero, so its momentum is zero, and the only momentum contribution is from the particle, which is equal to mvx. And I'll write plus so as to indicate the direction of momentum, because momentum is a vector. And so that's all the momentum that's going to be there before the collision. And after the collision, the momentum, again the wall is stationary, so there is no momentum contribution from the wall, but there's the momentum of the momentum, there will be a momentum contribution coming from the reflected particle. And if I assume the uh, 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 just a minute, yeah, so if we assume that the velocity of this particle after the collision has happened with the wall, if I say that is u, right, u, so then what is the balance? So this is all the momentum that's going to be there after the collision. Now the balance of linear momentum says that this, and I will not write a sign here, I'll just assume that this u contains the sign, whatever it is, the equation should give me the sign, right? So the balance of the law balance of linear momentum says that the total momentum should be conserved, which means the total momentum before the collision, which is uh, plus m vx should be equal to, let me write a u of x here, should be equal to the total momentum after the collision, right? And after the collision, sorry, the balance of linear momentum says that the total momentum of the system is conserved. Now, if u is the velocity, but this velocity will point in the other direction, right? Because it's getting reflected now. So then from these two equations, I get that v of x is equal to minus times u of x. Okay. So basically in magnitude they will be the same, but it will be opposite in direction. That's what it tells us. Now if we can calculate the change in momentum, okay, change in momentum. And this change in momentum is going to be equal to initial momentum minus the final momentum. So initial momentum was m vx minus the final momentum is again minus times mvx, right? So that's going to be equal to twice mvx. And what is the total time in which this momentum change happens, right? If this distance is L, if this total distance is L and the particle travels from, let's say, this end to this end, and so the time consumed in this travel would be L, the length, divided by the speed, right, which is v of x. Now, what is the time interval between two successive collisions between for this wall, right? If we look at this wall, let's say there's a particle which strikes this wall. Now that particle will be reflected, so it will go back and it will travel a distance L, and then it will again travel with the same, it will get reflected from this wall, and then it will travel the same distance L again and hit the wall again. So between two successive collisions on this wall, the time would be, the time elapsed would be 2L divided by v of x, right? So we will take this, let me keep it here, and I will say t is equal to 2L divided by v of x. So I'll just rewrite it here. Time taken between two successive collisions is 2L upon Vx, right? And now what is the rate of change of momentum? So in this time interval that we calculated, this is the momentum change that's happening from the wall's perspective, right? So the total rate of change of momentum would be equal to twice mvx divided by 2L, and then v of x will be multiplied here, right? So that is equal to, if we simplify, 2 and 2 will get cancelled out, it will be m vx squared by 2. Okay, So now this is the rate of change of momentum. But what does Newton's law tell us? Newton's law tells us that the force experienced by a body is equal to the rate of change of momentum of that body, right? So this quantity here, okay, I think someone has a question. Yes, Radha Narayanan. Am I audible? Someone has raised a hand. You want to ask something? You can also type your question or query in the chat box. Can you hear me, Radha? Let me do a quick audio check if everything is going fine. Yes. So I am able to, okay. L is missing in denominator. Oh, thank you so much. Yeah, you're right. You're right. So there will be also this L will carry over, right? As rightly pointed out by Radha. There won't be a 2, but there will be L. There will be no 2. Yeah, thank you. Thank you, Radha. So this is the rate of change of momentum, and now this would be the force experienced by this wall. Okay, that's what the Newton's second law tells us. Now this force, this is being applied by just one particle, right? And if we assume that there are n such particles, right? If we assume n such particles, then the total force will be summation of I runs from 1 to n m vxi squared upon L, right? Where this vxi is uh, the velocity, the x component of velocity of the ith particle, right? The x component of the velocity for ith particle, and we are summing over I from as I goes from 1 to n. So this is going to be the total force. Now m and l, these are constants. We assume that all of the particles have the same mass, so we can pull them out of the summation sign. So I'll write this force as F now. This is going to be equal to m upon L summation of I runs from 1 to n Vxi squared, right? And this quantity, further we can do one more thing. What we can do is we can add and divide. Yeah, sorry, we can divide and multiply by n, right? So this is equal to m times n upon L summation of I runs from 1 to n, Vxi squared divided by n. Okay, and this will be, I'll write it as m n upon L, and I'll write this quantity here in these brackets, and this is called a mean square velocity, right? Mean square velocity. So we are not assuming here that every particle has the same component of velocity in the x direction. These could be different, right? But this quantity here, Vxi square, in these brackets, it means that we are taking some kind of an average velocity which defines this cube of particles, right? And this is going to be the force exerted by these particles on the wall, right? So now if we want to calculate the pressure, how do we calculate pressure from force? We just divide it by the cross-sectional area, and in our case the cross-sectional area is going to be L squared, because it's a cube, and in cube each side has the area L squared. So we can divide by that factor to find that the pressure exerted on the wall is nothing but, if we divide by L squared, there's an L already there, we will get L cube, and we will get Vxi, or I can drop the I now. I'll just write it as this quantity, and it's self-explanatory what this quantity is, right? This represents the mean square velocity or mean square speed. And further, this n can be broken down. This n here, we can write this n as n times Na, okay, where this n is the number of moles and this Na is the Avogadro's number. So if we make that substitution, we will get that P is equal to m n Na divided by L cube times the square of uh, mean square velocity. Okay, and furthermore, now here's one important point. We are only considering, in this equation we have only considered the x component of the velocity. In general, the velocity doesn't need to be only along x, it can have other components as well, vx, vy, vz, right? And what we assume is that since all the motion of all the particles is random, right? So at any given time, if we pick randomly one particular particle, we assume that its velocity is equal in all directions, right? So the component, so if total velocity v, so now we are going to 3 dimensions here. If total velocity v is equal to, let's say, Vx along I plus Vy along j plus Vz along k, what we assume is that Vx square is equal to Vy square is equal to Vz square, right? Now this is also called the law of equipartition of energy, okay, or this assumption at least leads to that. We assume that the at any given point, because it's a cube, it doesn't matter which face you take, you will get the same result on every face, right? So if we make this assumption, then we can say that v square, which is the magnitude of the vector now, this velocity vector, right, it is equal to so when we write magnitude, then the vector signs will drop, and it will be like Vx square plus Vy square plus Vz square, and using this we can write that V square is equal to 3 times Vx square. So Vx squared is equal to V square by 3, right? And now, so we can write that if we average over these velocities for all particles, okay, this is for single particle, this is averaged for all particles, we will get this relation, okay. And this V here is also called, as I said, the V square is the mean square speed or mean square velocity. The V itself, so V square is mean square, let me call it speed, and then V is root mean square velocity, right? Root mean, let's write velocity, not speed, because we are talking about definite directions here. It will be root mean square velocity, right? And now we substitute this back here, right? We substitute this back here, and the equation for pressure comes out to be P equals M N N A, and now instead of V square we will have V RMS square divided by, now we have L cube here, I am going to replace it by V because it's the volume, and there will be a 3 coming from this substitution, okay. And a slight rearrangement gives PV is equal to M N N A divided by 3 V RMS square, right? Now we know from, for example, from Charles' law, we know that pressure uh, is inversely proportional to temperature, and from Boyle's law, we know that pressure is inversely proportional to volume. So if we put all together that, we get the ideal equation, ideal gas equation, that PV is also equal to nRT. Okay, so this comes from the ideal gas equation, which is basically, if we put together all those laws, the Charles law, Boyle's law, and there's one more, it's called Gay-Lussac's law, right? So if we put all that together, we get this equation, and this equation is obtained if we treat the particles of this gas as like, it's called the kinetic theory, right? This one comes from kinetic theory. Kinetic theory, and this one, this equation, which relates PV to nRT, this comes from observation experiments, and so this is called a pheno these type of equations are called phenomenological, right? They are observed and then written down, while this one comes from reasoning, right? We have developed this. So but now the question is that these two should be equal because they represent the same quantity, right? So if we take these two equations, what we can write from here is uh, VRMS. We get an expression for VRMS as, let's calculate VRMS squared. So n and n will cancel out, this n and this n. We will have 3RT divided by M N A. Anything else? No, right? And Na is the Avogadro's number. So what is M times Na? It becomes the molar mass, right? Because Na is 1 mole. Na is 1 mole, and M is the mass of each particle for that mole. So M times Na represents the total mass of 1 mole, which is called the molar mass. So this comes out to be 3RT by M, capital M, right? So I'll just write a few more equations. So if we look at again, uh, if we look at, let's say, yeah, this equation itself, right? So let's try to get few more quantities from here. Now, if I were to write, if I take this m here and then multiply everything by half, what I will get is 1/2 of m Vrms square. This is equal to 3 by 2 RT upon NA, right? I have just transposed this m here and then multiplied both sides by half. Now this quantity here, this is the average kinetic energy of one particle, right? One particle. And this is equal to 3 by 2, and this R, which is the gas constant, divided by Na, it's called the Boltzmann constant, Kb, right? This does not depend on pressure or volume or anything. These are constants. So we find that average kinetic energy of one particle is equal to 3 by 2 Kb, it's the Boltzmann constant, times temperature. Okay, and now if we have to write the energy of entire system, okay, let me write it: average kinetic energy of gas, average kinetic energy of gas, all the particles, right? I just take this energy and multiply it with what? The total number of particles, right? So this average kinetic energy of gas is equal to 3 by 2 times, let's say, some NF kBT, right? Where NF is what? Or let me just call it N for now, just to be consistent with our previous notation. Here N represents the total number of particles. Total number of particles. Now if we want to find the energy density, okay, we define another quantity called the energy density, and which is defined as average kinetic energy per unit volume. Okay, so in a unit volume, how much of uh, energy is kinetic energy is contained? This will be 3 by 2, and here this N will be now, so we'll have to just basically divide by volume, right? N by V, and then I can rewrite this whole thing as some NV, where NV is nothing but number of particles in unit volume. Number of particles in unit volume, right? So this quantity is going to be of interest to us, right? So this is the average kinetic, because now it defines the thermal energy of the system. I think we mentioned in first or second class that the thermal energy of the system is nothing but the kinetic energy possessed or contained by its molecules or atoms or whatever constitutes that gas, right? So this is the average kinetic energy now, and we can see that this kinetic energy depends on temperature. So if the temperature goes up, the average kinetic energy goes up, right? This is the absolute temperature here, T. So this is one, and the other quantity that we can define here is, so let's call this E, okay? This average kinetic energy per unit volume, or the energy density for short. Let's call it E. So E will be equal to this quantity here. Please feel free to ask questions if you have any, or if you want me to repeat. Okay, so this is E. We can also define dE by dt. dE by dt would be what? Rate of change of this energy. rate of change of this energy with respect to temperature, right? And this will be simply equal to 3 by 2 nv, the number of particles in unit volume. This does not depend on temperature, so it's a constant if we differentiate this quantity with respect to time. Kb, again, Boltzmann constant, it's a constant, so it will come out of differentiation. And then t, dt by dt is 1, right? So this will be the rate of change of this energy density, and this is called actually CV. Okay, it's CV means heat capacity, and since we are calculating it on a per volume basis, so this will be volumetric heat capacity. Volumetric heat capacity. Okay, so volumetric heat capacity, it's nothing but the rate of change of internal energy with respect to temperature. And this is a very famous relationship that you often encounter in thermodynamics as well. That CV, there you call it specific heat, right? This is equal to del U by del T. And you would have seen this in your thermodynamics courses. So this is the origin of this volumetric heat capacity from the kinetic theory of gases perspective. Now, why are we doing this all? We have to, so our objective is to model conduction, right? So now what we want to say is that this all is applicable even to electrons. What I mean by that is that instead of a molecule or an atom, if this particle was an electron, then all of these results would apply, right? So the final expressions that we derived here, these are applicable even to electrons. Okay, so applicable to electrons. But how do electrons form ideal gas, right? Because these are ideal gas equations. Why on earth would we relate electrons to a gas, right? That's the question. So that's why I said in the beginning that this discussion is being done with the assumption that we are discussing metallic solids. So what happens in metallic solids? Imagine this is some solid. So in metallic solids, what the situation looks like this. Okay, so we have these atoms, which are not atoms, but these are ions, right? Or they are called kernels, and these are positively charged. And metals have valence electrons in their valence band, right? So these electrons would be roaming everywhere. Right? So this model is often understood as follows, that instead of having these electrons revolve around their own atoms, we assume that there's a gas cloud. Okay, we assume that there is a gas cloud which is made by these electrons, which is contained within the boundary of the material. So if this is, for example, say a bar of copper, right? So this gas does not exist beyond the boundaries of the sample, but within the boundaries, this is how the situation looks like. It behaves as if there's a gas of electrons which is freely moving in the within the sample, and there are positive ions which are stationary, more or less, right? They are fixed to their positions, but they can just vibrate about their mean position. The electrons are free to move around the sample. So if we take, for example, a point here, We cannot say that this electron was lost by this atom or this atom or this atom or this atom. So we basically, this is a very non-local flow of electrons in this uh, uh, like within this boundary. So that's why it's called a free electron gas. Free electron gas. It behaves like a gas, or at least in our model, it will behave like a gas, right? So now what we want to do is we want to use that ideal gas theory to apply it to electrons and find some properties about conduction and all that, electronic conduction, right? So this ideal gas theory will basically help us to devise a model to understand the electronic conduction and much more, right? As we will see. But before we go there, let's look at some questions, okay? Some problems, and you can answer these problems, right? So I'll just write the problems and you can try to answer them, okay? So these will be MCQs. So this is the first one. So the atoms in a metal behave like, okay, this is what we were discussing till now. A, they form an ideal gas. B, they are fixed in position. They behave like a liquid. And D, they are rigidly fixed and can never move, right? So here I will add an option like this. So which of these do you think is the correct option? Can you, is the question visible to you? Okay, Pradeep says it's D. Okay, uh, D. Okay, let's see what D is. They are rigidly fixed and can never move. Okay, okay, that's one answer. Would you like to try, Radha, if you are there? Okay, so see, the question is, what do the atoms behave like, right? So if we go back to this picture here, right? So atoms are fixed in their position, but they are not rigidly fixed, right? What that means is they can vibrate here, just like this, in such a way that, so let's say this is one atom, let's say this is one atom, right? So it can only move this much. These are its two bounds. Okay, I'm just showing for the sake of example, and within this bound the atom can just vibrate like this. Okay, I don't know if the video is smooth enough for you to see. So it can only vibrate here. Okay, but its average position, right, if you consider its center of mass, right, that will always be fixed between these two lines, somewhere around here. So this is the center of mass. So atoms can only vibrate about their fixed position. The mean position is fixed, but they are not rigidly fixed. Rigidly fixed means if they are here, they will continue to be here. They will not rotate, they will not vibrate, they will not do anything. Okay, so the correct answer for this question is option B. They are fixed in positions but vibrate about their mean position. Okay, if they were rigidly fixed and can never move, then uh, that's not correct, right? Because in that case, the atom would have no energy at all. If it does not even vibrate, then you can't really say how you can't define temperature, right? Temperature is defined from the vibration of atoms, but the vibration happens in such a way that the mean position, the average position gets fixed. Okay, let's move on to next one. uh, Question 2. Okay, this is a good question, I guess. So relative to the volume of metallic solid, the amount of vacant space within the solid is of the order of. Okay, this might be a little tougher to answer because I did not discuss it, but let's discuss it through this question. 40%. So these are the options, okay? 1%, 10%, 40%, or 90%. So the question is relative to the volume of metallic solid. Okay, so volume of metallic solid means this entire volume. Okay, all of the space here, everything, which whatever is inside the boundary. Now the question is asking that relative to this volume, what is the amount of vacant space? Vacant space means the space without these uh, the what's it called, the interionic space. Okay, if we just leave these exclude these ions, what is the remaining space? What is the fraction of that space related to the total? That's what the question is asking. So what do you think is the correct answer, or any guesses? You want to try, Pradeep? So the question here, like we did not discuss in particular, but it depends on crystal structure. Crystal structure and what's called the atomic packing fraction. Okay, so what does that mean? It means that if there's a simple cubic structure, okay, how do I draw a simple cube? Maybe something like this. Okay, this is a simple cubic structure. In a simple cubic structure, the atoms are placed only at the corners, corners of the unit cell. This drawing is not very accurate, so these are supposed to touch each other. Okay, so these two touch. Similarly, these two also touch. Okay, I hope you understand what I'm trying to draw here. So neighboring atoms touch each other. So for example, if we look at this one, uh, if we look at this particular atom, it has two neighbors. One neighbor is this, the one here, and one neighbor is this. And these two are in touch. These two are in touch, right? So if we were to look from the top, it would look something like this. Okay, something like this if we look from top. So this kind of an arrangement, and similarly there are atoms here at these four positions as well. Now this is called a simple cubic packing. Okay, there can be other type of packing which is called, so this is simple cubic. There is another type of packing which is called a face centered cubic. Okay, FCC, what we call FCC. So in that what happens is the top face, which was looking like that, the one above, now it looks like this, right? So this was the top face here, and now this top face looks like this, and every face will look like this. Okay, this is called a face centered cubic. Face centered cubic. So depending, and similarly there are many more atomic arrangements, and depending upon which kind of atomic arrangement you have, there are different kinds of packing fractions. Now what does a packing fraction mean? A packing fraction means, for example, look at this space, right? This face which is made by the centers of these four atoms. Now this space is not entirely occupied by these atoms, right? There's a free space in between, which is right here. And similarly, if you like draw other four as well, if we draw the other four circles as well, something like this, this, and this, we see that there's a space left in between, which is empty. This is not occupied by atoms. So it means that as inside a solid, all of the space is not occupied. There's a lot of free space inside the solid. And this is the space, this free space. This is the one in which electrons, such as these, right? What we drew here. So this is that in between space in which the electrons can roam about and behave like a gas. So this, if we, so now the packing fraction means basically it's the ratio of how much space is free divided by the total volume. Okay, the volume which is free unoccupied divided by the total volume. And depending on which kind of packing we have, which kind of structure we have different kinds of different values of this ratio. Okay, but around roughly, if we have these four options, the correct option is around 40% of the space is free. Okay, for some it can be 48%, for some other structures it can be 35%, 36%. So but roughly it's around 40%. Okay, so this is the free space. Now maybe let's look at one final uh, actually let's do one numerical. Okay, a numerical problem. So if we assume an ideal gas, so this is a question 3. Assume an ideal gas, let's say argon. Assume argon as an ideal gas. at STP. Now what does STP mean? Standard temperature and pressure. And what's that? Standard temperature and pressure is 0 degrees centigrade and 1 atmosphere pressure. So these are called STP conditions. So the question is, if we assume that argon behaves like an ideal gas at STP, what is its specific heat? What is its specific heat at constant volume? Okay, and we actually define this quantity. So what is given? Argon, we are given argon is a gas and it's at standard temperature and pressure, and what is its specific heat. Now it may appear like that we don't have much data given in the question, but actually from if we look at the kinetic theory of gases, we have everything. So let's see what we have. We actually derived an expression for this, right? CV, this is the volumetric heat capacity, right? So if we take this, so we know that CV is equal to this. CV is equal to this. Okay. So the question now is, how do I calculate this number? Right? Because KB is a Boltzmann constant. I know its value. The question is, how do I calculate NV? Okay. So NV can be calculated as follows. So first thing that we realize is that uh, so we recall. Let me write it. The solution is this. Solution to this question. Okay. So recall that every ideal gas at STP occupies 22.4 liters of volume. Okay, so it occupies this much of volume. Then it means that every mole, every mole of an ideal gas, okay, 1 mole at STP occupies this much volume, which means that 1 mole, that means how many atoms? Avogadro's number, right? 6.022 into 10 power 23 atoms of argon occupy 22.4 liters. Now I will convert it into meter cube. So this many meter cube of volume. So I have done two things here. I have written 1 mole in terms of atoms and the volume in terms of meter cube. Now, okay, so what are the uh, number of atoms per meter cube? That's what we need, right? Because this NV means number of atoms or number of particles per unit volume, and that's what we are calculating here. In the argon gas, what are the number of atoms per meter cube? And we can get it from this relation. This will be equal to, see, these many meter cube has this many atoms, right? So 1 meter cube would be this divided by 22.4 into 10 power minus 3 number of atoms, right? So number of atoms per meter cube would be 6.022 into 10 power 23 divided by 22.4 into 10 power minus 3. Okay, and then CV will be equal to, now you can calculate it, it will be 3 by 2 times this number times uh, the gas constant. Okay, sorry, the Boltzmann constant, Kb, right, from here, Kb. So the value of Kb is 1.38 times 10 to the power minus 23 in SI units. Okay, and if you evaluate it, you will get roughly 0.55. uh, no, you will actually get 0.55 into 10 power 3, let's say around 550 joules per meter cube Kelvin. Okay, this is what you will get. So this is the answer to this question. So similarly, let's say there's a follow-up question. This is question 3. Now question 4 says that what is the thermal energy per unit volume? What is the thermal energy per unit volume for argon at STP? So how do we calculate that? Well, the formula is really simple. If we go back, I told you the thermal energy per unit volume, that is this quantity here, right? And what is the difference between this quantity and this quantity? Only temperature. So we have already computed what this is. We just have to uh, multiply it with temperature, and that will give us the energy density. Okay, so this will be equal to 550, what we got earlier, joule per meter cube, times temperature. What is the temperature? 0 degrees Celsius, right? So the energy density will be 0. Is it correct? Have I done correct calculation here? Will the energy density be 0? Does it make sense for energy density to be 0? Yes, Radha. Yes, Radha, you can speak. Am I audible, Radha? Or you can write here. You can type in the chat box if you want to make any comment or suggestion. So this is supposed to be an interactive session. I have to make sure that you If you understand, then you say so, or if you don't understand, you at least ask me your doubts. So have I done here, have I computed it correctly? Okay, so what we have done here is not correct actually. So this temperature, although we are given that temperature is 0 degrees centigrade, we commented that this temperature has to be written in terms of absolute temperature. Absolute temperature. And absolute temperature is always given in Kelvin. Okay, so instead of 270 degrees, 0 degrees centigrade, it will be 273.15 or roughly 273 Kelvin. And you also have one Kelvin here, right? So the Kelvin and Kelvin will cancel out, and you will get somewhere around 1.5 into 10 to the power 4, roughly around this value, joules per meter cube. Okay, this will be the answer to this question. Okay, any doubts? Yes, Radha, you want to speak?
No, I didn't know how to message or speak. I
Oh,
was
I see.
thinking of that zero to should be in absolute, not in centigrade. I wanted to convey that, but I didn't know how to convey. I
I
didn't know how to message or speak.
I see. I think you tried to speak a couple of times earlier in the video as well.
I don't
Earlier
know
in the
where to click.
I see, I see. So you found it now, the button.
Now you can hear me, right?
Yes, yes, I can hear you clearly.
Yeah, okay, fine.
So
Thank you.
I have corrected this. I just want to test that whether the concept is clear, right? So we have to write it in terms of absolute temperatures. You are absolutely right. So yeah, so this is what the energy density would be. Now I want to uh, go to the Drude model. Okay. Do you have any questions, by the way, Radha, uh, about what
No,
we
sir.
have
No, sir.
discussed? Okay. Okay. Just ask me anytime. You can stop me and ask your question. So now we will go to the Drude model. Okay. Now what is Drude model about? Now Drude model, it predicts the electronic conductivity. Conductivity. It predicts the electronic conductivity uh, or exhibited by a metallic solid by treating electrons as free electron gas. Okay, so what this Drude model does is, so this is its first application. I'm just letting you know what the application is before I tell you what the model itself is. So now we saw that this is the situation inside a metallic solid. So this is the situation inside a metallic solid, right? And now if we apply some electric field or we apply some potential, let's say that we have a battery here. We say we have a battery and we are connecting the positive terminal to one end of the this solid and negative terminal to another end of the solid. Okay. Now what will happen is the current will start to flow in the circuit because this this sample has free electrons, right? So the direction of current is given from positive to negative, while as the motion of electrons will be this way, right? So electrons will move here in this way. Electrons. Let me point it here. Electrons will move here, while the conventional current will move in this direction. Okay, so there will be a conductivity set up in this material because of this potential difference, right? And now we know that the electrons behave as a free gas, and they will it's their average properties that will establish this conductivity, and we want to find what that conductivity is. So first we note some basics that we all know. First we will start from Ohm's law. Okay, what does Ohm's law say? Ohm's law says that potential difference is equal to the current times the resistance. Okay, it basically says the current is proportional to the potential difference, and then R comes as a constant of proportionality. Now this resistance itself, what we can see is that this resistance is directly proportional to the length of the conductor. Okay, if this conductor is long, let's say this is its length, the longer the conductor, more resistance it offers to the traveling charges, right? And so this is there's a direct proportionality here, and it's inversely proportional to the area of cross-sectional area of the conductor. Okay, and this proportionality is eliminated by introducing a constant which is called resistivity. So we write that R is equal to rho times L upon A, where rho is resistivity. And while the resistance depends on the type of, sorry, the shape and size of the sample, resistivity is a material property. It's independent of these characteristics, right? It only depends on the material you are using. So this is this is the quantity of interest to us because we are also interested in knowing the material behavior rather than studying few shapes and samples, right? Particular shapes. So so we define another quantity which is called conductance. Conductance or conductivity? Sorry, conductivity. Conductivity, we denote it by sigma, and it's equal to, we define it to be the inverse of resistivity, which will be equal to L by Ra. Okay, this is the conductivity. Now we can substitute it in the Ohm's law to get that, or using in Ohm's law, we find that V is equal to I times R. Now I can replace that R by rho L by A, right? And then I can divide by L on both sides to find that V by L is equal to I rho by A okay, and this V by L is nothing but the electric field. Okay, I'm going to maybe use a big epsilon for the electric field. So if there's a conductor of length L and we apply a potential difference of V across its ends, then the electric field set up in that conductor is the is given by V by L. Okay, and this is equal to, now I by A, this factor I by A, it means that current flowing through a unit cross section, unit area of the cross section, and this quantity is called current density, represented by J. And this is actually a vector quantity, but since we are talking only of one dimension here, so this will be a scalar quantity for our purposes. And then rho is conductivity. So this is an equivalent way to write the Ohm's law in terms of electric field and current density. So we can rewrite this again as J is equal to electric field times sigma, right? Because sigma is 1 over rho, and I will write it as, this is nothing but this is Ohm's law. Okay, so now we want to, so this is again a phenomenal, okay, I can't say this word. It's called phenomenological model, right? We are just observing, and based on our observations we write a law which is valid for a wide range of wide window of values. So this is called a phenomenological model, right? Now we want to inquire what what is the actual physics which gives rise to this, okay, which correlates with this observation of ours. So what we do is we again take this same sample of length L, okay, so this is my sample, its length is L, and what I do is I apply a voltage V across it such that there is an electric field set up. Now if there's an electron inside this, let's say there's an electron inside this electron inside this conductor, I want to calculate what is the force applied on that electron. Okay, now I know that force is equal to charge. Now I will represent the charge of an electron by E, and I will represent the field by, as before. Now force is equal to field times the charge, so this will be the force applicable on the electron. Now I again know that this force will be equal to mass times change of velocity, dv by dt. Okay, so E is the, so what we are doing is, let me just repeat quickly, we are taking a conductor of length L, we are applying a potential difference across this, and let's say that there's one electron present inside this conductor. The force experienced by that electron would be charge times the field, right? So the charge of electron is represented by small e, the field strength is represented by capital E, and this field would be equal to V by L. Okay, and then we just write the Newton's law. Okay, this is Newton's second law. Newton's second law gives the definition for acceleration. Okay, so it says that the total force applied on electron is equal to mass times its acceleration. Now what we see here is that if we the acceleration is constant if the field is constant, right? Constant if this quantity is constant, right? Because this is constant, the charge of electron is constant, so if E is constant, then this whole thing has to be constant. It means that if we apply a constant electric field on a sample, then the charge should keep on accelerating, right? The acceleration is constant. That means the velocity should go higher and higher and higher in time. But that's not true, right? That's not what we experience in our daily observations. So something has to limit this process. The electron cannot accelerate infinitely. So there must be some kind of a resistive term, right? Which is true because this electron does not move freely inside this conductor. When it moves, it encounters collision with other electrons and as well as with the ions present inside this conductor. So to account for that resistance, we introduce a term which we call gamma. Okay, so I rewrite the first term, which is the inertial term, and then I add to it a term gamma times velocity. Okay, so this is a term which increases with velocity. Okay, as you increase the velocity, this term increases in magnitude. So it actually keeps a check because now the sum of these two has to be equal to this total force. Okay, so this term keeps this infinite acceleration in check. And so we get the equation from here. If we just transpose this to the other side, what we get is me times dv dt is equal to charge times electric field minus gamma times velocity. Okay, and from here we can find out when is acceleration 0. Okay, if acceleration is 0, then right hand side will be 0, right? So this quantity will be equal to gamma times v, or this gamma would be equal to v divided by E times the electric field. So this is the relation that we find. And now what we want to do is we want to put this back, this value of gamma, back into this differential equation, right? So what we will get is me times dv by dt. So this is the, like, we are deriving the Drude model here. Okay, dv dt is equal to E times the field minus gamma. So gamma is v, and then another v will multiply, so this will become v square divided by E times E. Oh, sorry, I have done the wrong, the computation wrong here. Gamma will be equal to E times epsilon by v. So when we multiply it here, v and v will cancel out. Oh, just a minute. Oh, not in this one. I want to substitute this gamma. Oh, maybe not, because this is a, yeah, so this is a particular value of gamma. So now what I want to do is, okay, I want to say that this acceleration will be 0 when this velocity corresponding to this acceleration has been achieved, and this is the constant velocity, right? Final velocity. So this quantity here v will be equal to vf. So this is the value of velocity which is finally achieved where uh, the whole conductor saturates, okay, and the acceleration of the electron does not increase further. So this value is called vf, or the final velocity. Okay, so now we can substitute it back because now this is not a variable but it's a constant, right? So now we can write mv dv by dt is equal to E times epsilon minus, if we substitute for gamma, we will get this, right? And I can again rewrite it as E times these two quantities as common, it will be 1 divided by 1 minus v divided by v over f. So we can, so this is becoming a differential equation in one variable now, and which we solve. So I'll just directly write the solution to this equation. Okay, if we solve this equation in the interest of time, I'll just directly write the solution. We get v is equal to vf times 1 minus exponential of minus t upon tau, where uh, tau is equal to m times vf over e times e. Okay, so this is the final expression. So let's try to plot it and then find out. So this tau is called the relaxation time. Okay, relaxation time, and this is the time, average time between two collisions. Okay, it's the time between two collisions. So what does this equation tell us? Okay, let's plot it and then try to understand what it is doing. So if we take this equation and plot it, the graph looks like this. So this is v over vf, and here we are plotting t. Okay, and let me plot it here. Okay, so if this is 1, this value where v is equal to vf, the graph looks something like this. Okay, so let's try to understand. Now from this equation, if we set t equal to 0, if we set t equal to 0, exponential of 0 is 1, and 1 minus 1 is 0. So that means v is 0. Okay, velocity turns out to be 0. And if we set t to infinity, what happens? This is e to the minus infinity. E to the minus infinity is 0. So v is equal to vf. Right? V goes to vf as t goes to infinity. That is exactly what we have shown here. When t is 0, the velocity itself is 0, and when t tends to infinity, the velocity also tends to vf, not to infinity. So this term, this gamma term, regularizes this equation. Okay, so now tau would be somewhere here, the relaxation time. Then there will be, if this is the time axis, this will be 2 times tau, 3 times tau, and so on. Right? So around 3 or 4 tau, the value of v is pretty close to this final value vf. So now what does this have to do with conductivity, right? Our job is to find conductivity. So conductivity, and this conductivity is only due to electrons. Okay, so this is electronic conductivity. This does not involve any other kind of charge carrier, for example, uh, let's say holes or ions. Okay, so the current density J is given by n times. So let's first write current density. So we know that the current density J is given by, so current density means current through a unit area. right? So this is given by NV times VF times E. So what does this say? So current density means, so first of all there has to be a charge, right? Because current is I by T, and I itself, the current, is equal to dq by dt. Oh, sorry. Current density is I by A, and this I is itself Q by T, Q by T into A, right? Now, if we, so this is the cross-sectional area, right? So if we multiply and divide by length, right? Roughly, I'm saying for the sake of dimensionality, we will find that this term here, okay, or let's say this term here is volume. So if this and this is velocity, okay. So Q by AL is some kind of a charge concentration per meter cube, okay, and L by T is velocity. Now Q itself can be written as N times E. If N is the number of particles and E is the charge on per each particle, then it can be written as N times E. And this quantity is NV, which is here. This quantity is velocity, which is here, and E here is as such. So that's why current density is written like this. And now we just substitute values because we have found the expressions for uh, uh, basically VF, okay. And if we substitute that, we find that this J is equal to NF times tau E square field divided by M. So this is the current density, okay. And now we can recall, we wrote Ohm's law, right? So this was Ohm's law. Now if we relate these two expressions, we find that this sigma is equal to NF E square tau divided by M. I'm sorry, I may have used NV earlier somewhere, so it's the same thing. NV, NF, these are the same quantities, okay. So this is now my sigma expression for conductivity. So this is what I wanted to derive, right? Conductivity from some elementary model which considers the physics of how electrons move under a potential. And this quantity, if I substitute the values, now NF, what does NF depend on? NF depends on number of, so NF is basically number of free electrons. Number of free electrons in unit volume, okay, so per unit volume. So what does it depend on? It depends on valency of the atom, valency of the metallic atom, okay. And what else does it depend on? That's pretty much it, right? And maybe the density of let's see, yeah, the density of the metal, right? If we know these two things, we can compute this value. So if we are given a particular element, we can compute what n of f is for a particular metal. And E is the charge on electron, which we already know. E is the charge on electron, which is 1.6 into 10 to the minus 19 coulombs. And tau, this relaxation time, which is the average time between the collisions, it hasn't been measured to be of the order of 10 to the minus 14 seconds. Okay, and m here, me is the mass of electron, which is again known. It is equal to 9.1 times 10 to the power minus 31 kgs, right? So if we know all these values, if we crunch in the values, we will find that sigma is of the order of 10 to the power 6 SI units. Okay, and SI units are this inverse of ohm meter, okay, per ohm per meter. So this value of sigma computed from this model, which is the Drude model, it is very close, so it agrees well with the experimental or experimentally determined values for metals, okay, and what is this agreement? Agreement is in terms of order of magnitude. Okay, so for several metals, the conductivity is of the order of 10 power 6 per ohm per meter. Okay, order of magnitude. So this shows the applicability or the success of Drude model in explaining the conductivity of a metallic specimen, and it does so by treating the electrons as a gas cloud, obeying uh, uh, the ideal gas equations. Now the only catch here is that this is not always applicable, because if we look at the density of electrons, let's say 1 mole of a substance that has free electrons of the order of 10 power 28 electrons per mole, right? But at the same number, at same time, if we look at the Avogadro's number, that is 10 to the power 23. So basically, there are 1,000 times more electrons, more free electrons present in a metallic specimen than what is predicted by or what is required by the ideal gas equations. So we have to be a little careful in applying these equations, but overall, like, it doesn't do so badly. The model predicts the value to a reasonable degree of agreement. Okay, and similarly for thermal conductivity as well. So for thermal conductivity, if we follow a very similar process for thermal conductivity, right, we find the expression. So I'm just going to write the expression here. The derivation is in the chapters, sorry, in the lectures online. You can check that. Uh, we don't have much time left for this session, otherwise I would have derived it. So the expression is, it goes like this, okay, tau times CVE. Okay, I'll just explain different terms here. And this is also called Drude model. It's Drude model for thermal conductivity. Okay, so this V square here is, again, V is the root mean square velocity, root mean square velocity. Tau is again the relaxation time, average relaxation time, which is the time between two collisions. And CVE, now this is an important quantity, okay? It's the contribution to specific heat capacity from electrons. So there are going to be in general two contributions to this specific heat. One is coming from ions and one is coming from electrons. Okay, and this is only the part, the contribution which is contributed by electrons, not sorry, yeah, by the electrons, not the ions. Okay, so yeah, this is the equation that is predicted by the Drude model. Okay, so okay, so if we compare it, so what is the K? Sorry, we forgot to define K, which is the important parameter here. K is thermal conductivity. Thermal conductivity. And what is thermal conductivity? Like it's defined as flux per unit. So it's a heat flux. This is how I remember it. Heat flux per unit time per unit thermal gradient. Okay, which means that K should have an expression like minus times. So heat flux means Q upon A, and per unit time is this, and then per unit thermal gradient. Okay, so we can write here dx by dt for a one-dimensional model. Okay, and the negative sign basically it's consistent with the second law of thermodynamics, which gives the direction of spontaneous heat transfer. Okay, so so what does Drude model do here? So once we get this expression, we again plug in the values. We know what's the uh, value of tau. We know the value of CVE. How do we know the value of CVE? It is computed to be, so all these quantities are like coming from experiments. Okay, so CVE, there are some experimental techniques which allow us to measure the contribution of to the specific heat just from the electronic conduction. Okay, which is just coming from the collision of electrons. So from those experiments we know that this is of the order of 10 power 6. Tau is again of the order of 10 to the minus 14. And what else? Yeah, so this RMS root mean square velocity. Now it's not a root, it's just mean square speed. It's equal to 10 to the 10. Okay, and the units will be square of the speed, right? So if we plug in all the values, what we get the value of thermal conductivity to be is, so K comes out to be of the order of 100 watt per meter per Kelvin. Okay, and this is again this order of magnitude here is again very close to what we observe experimentally in for different materials as well, for different metals. So this is how the Drude model takes into account the electrons, considers them as ideal gases, uh, considers them as a gas, an electron gas, where each electron behaves like a molecule or an atom of an ideal gas, and then predicts the average properties that come out. So the properties, two properties we saw here in this lecture, one was the thermal conductivity and the other was the electronic conductivity, right, sigma. And we found that the computed expressions give us the results which have the same order of magnitude as that computed with the experiments. So this model bears a, like it gives us a reasonably good agreement between the experimental values and the computed values. So that gives us the that basically it establishes the credibility of the truth model, right? But there is a catch here as well. So actually, if we the Drude model does not predict all values satisfactorily, okay, or to a satisfactory degree of agreement. For example, if we look at the terms like mobility, electron mobility, okay, mobility, or if we look at this heat capacity, right, CVE, okay, the values. So in one case, the values predicted by this Drude model are 100 times more than those observed in experiments, and in the other case they are 100 times smaller than those predicted in the experiments, right? So it does. So for some quantities, it computes these the actual values to reasonably good degree of agreement. For whereas for this at the same time for some other quantities, the prediction does not hold as well, right? And it's only when these two quantities are multiplied together in some quantity, let's say some physical quantity which is defined as product of these two, or effectively which can be rewritten as a product of these two, those quantities that these two effects cancel each other, and the prediction comes out to be very close to the experimentally observed values. But apart from those scenarios, it doesn't always work. So the bottom line is that Drude model, Drude model is useful, but not always accurate. Okay, useful as in it can predict the trends of thermal conductivity and electronic conductivity to a very good level of agreement, but at the same time there are some quantities in which the error is of the order of 10 power 2, right? There are two orders of magnitude difference between the two values, right? So this is not always accurate. So these models should be used to understand the qualitative behavior rather than the quantitative behavior of the model, right? So with this, I'll stop this session, and I'll see you in the next session a new discussion, probably on the Maxwell-Boltzmann statistics. So yeah, thank you for being with me.